So this is pretty neat. I thought I'd share it with you guys. Been playing around with some deep learning ideas on this coronavirus weekend, and I thought somebody else might find it interesting. Um, so just going back to basics. I'm using this tool that we've developed. You don't have to use this. You can use any other framework, but I think it's good for visualization and explaining stuff. So I'm going to use it here, but everything I'm talking about, you can use it in TensorFlow, PyTorch, or whatever. So just looking at some basic network, just something as an example. This is not Linnet. Obviously, it's more complicated. There's a couple convolutions, a max pool, and just trying to exercise all the units. There's a batch norm and scale in there too, and then there's an average pooling on the end, an 8x8 average pooling like you got at the end of ResNet or something, and then there's obviously a fully connected, and then it goes to a 10 deep output for the different classifications in MNIST. Then we're going to give it the MNIST data. I'm going to slow down the learning rate so we can see what's happening. Now, so just looking at something like this, it will learn. It'll start to pick up the different numbers, and the learning and the cost function will go down. You can see here the learning, with this learning rate, how the error is going down. If we pause at any point here, it's getting a lot of stuff wrong. It thinks that's a 4. That's an 8, it thinks. Got that 7 right, 7. So it's not really doing well. Let it run a little bit longer. Okay, so here you can see the error has gone quite a bit down compared to what it started out at, almost 1/10, and it should be doing pretty well. Let's see. Now the problem is here, actually, so it's difficult to find one that it gets wrong. Okay, so let's take a look at something that it gets wrong. The problem here is, well, okay, so this is like a weird, but if we look at what's going on in the pipeline, it's very difficult to tell it that this is where you went wrong. I mean, and the worst part of it is when you get down to the near the end, this fully connected, when you scroll through it, it's just taking a spectrum of all the features. It's just basically it's just taking a sum of all of the features and saying if you have these features together, then it's probably this number. Otherwise, it's not. There's no way to tell it, hey, you got this wrong, this is why you did it wrong, and here's how to correct it. There's just no way to do it. You can give it a small, so what will happen in the training is that it will give small nudges. It'll push in the right direction, so if you have a lot of those mistakes, they'll eventually get corrected. But that's not the way you teach, for instance, a kid how, if it got that number wrong, how to correct it. You don't give little nudges over and over again. You go and sit down, figure out where they got it wrong. And that's the problem with these current deep learning networks. And this is a really simple example. You look at more complicated things like ResNet and GoogleNet, they're all basically doing the same thing. It's just 1,000 little nudges in the right direction, but you can't find a case where it got something wrong and specifically tell it how to not make that mistake again. And that's a fundamental flaw in this type of backprop training. So in this experiment, I want to look at how we could maybe go about doing this a little bit differently. So in this video, I want to see, is there a different approach to maybe doing this instead of just grabbing all the features, a histogram basically of all the features, and saying if you have these features in the image, then you're likely to be this, otherwise you're that. And take maybe a more intelligent approach by extracting the features one by one and iterating over the image and modifying something that I'm going to call, I like to call the Visuospatial Sketchpad. It comes from brains psychology and stuff. So let's take a step back. Instead of directly jumping in and looking at the MNIST number data and trying to train a network to do that, let's take a step back and try to train it to be able to follow lines and detect lines and curves, and then in a background layer of the network start forming a description of how those different components are connected together, and from that come up with a description of how each of these numbers should be represented. In that way, you're giving the network a specific description of what each one of these numbers how they should be seen. Okay, so this time, instead of giving it directly the MNIST data, I've auto-generated some other example data. It's just a bunch of dots, and the training data for each image, there's one dot in the screen in a 32 by 32 image, and the training data is basically the X and Y coordinates of that dot, and so we want the network to start to learn that it has to identify the position of the dot in the screen. And so using the same basic network that we had from before, I'm going to modify it so that it does everything just like it was doing before. It takes a 32 by 32 as input, goes through the exact same layers, but then instead of giving a 10 output classification, it's going to do a logistic regression, give the try to predict the X and Y coordinates of the dot in the screen. Now, this network is obviously overkill for what we're doing here, but I'm going to expand on it. It's going to do some more complicated stuff, so we're just going to stick with this for now. Okay, so let's start the training, and I'm going to pause it right at the beginning. So we can see, you can see it's kind of right out the gate, even just with a few iterations of training, it's already kind of getting what it's supposed to be doing. So here the blue dot indicates the position of the in the data being given, and the red is what it predicted. So you can see it's kind of close. It's getting what it has to be doing. So we're just going to leave it for now. The cost function should go down pretty fast as we pause it here. Stuff is getting closer, and so the red dot is getting closer and closer to the blue dot. And we can play around with this more, get, more, with a better network and, tweaking the learning and momentum. Obviously, we could probably do this faster, but I don't care about that right now. Okay, so this is kind of starting to plateau. It seems like there's always a little bit of distance. It really gets it exactly right. Maybe we can leave it to run a little bit more. The cost does seem to have plateaued. In any case, okay, so we can save this now. Okay, so that's pretty easy. We can learn the position of the dot in the screen. So now the next thing, let's make it a little bit more complicated. If we give it 2 dots in the screen and we want it to identify the position of the dot closest to the top left corner of the image, we want it to learn that. Okay, so this time, instead of giving it 1 dot, we want to give it 2 dots. So we're going to amp it up a bit and make it a little bit more complicated. And let's see how it does with this. And there's a reason why I'm doing this. We'll get to that. But so I've generated some data that instead of 1 dot, now it's 2 dots. That's basically the difference, and we want it. And the training data will give it the coordinates of the top left dot. And let's see if it can learn that. So let's pause. So here you can see, obviously this is the one closer to the top left corner, but it's predicting this one. So it's going to have a tougher time. It is kind of tracking. This is clearly off, so it needs to run for a bit. So this is obviously a trickier thing to learn. But the cost function does go down pretty fast. Okay, so it's already starting. To kind of get it. Still a lot of mistakes though. Okay, so if I pause it now, it should be much better. So now it's doing a pretty good job. There's no weird stuff where it's in the middle or off in the woods. So this is pretty impressive right now. It's taking these 2 dots in the screen and then it's able to track. It's learned that it's supposed to identify the one closer to the top left corner. And by the way, there's no overfitting with this data because the number of images, you can see it hasn't even gone through 1 epoch yet. There's basically, it's covering all the possible scenarios with a certain, there's a limit. We don't want the 2 dots to be too close to each other. So there is a minimum distance, but then beyond that, all of the scenarios for 2 dots on the screen have been covered, so there's no overfitting. Okay, so now let's make it a little bit more complicated. Instead of giving it just 2 dots in the screen, we're going to add another layer to the input. And in that layer, we're going to also give it a dot. There could be another dot in that layer that's going to overlap with the one that's in the top left corner. And what we want it to do is, if there is nothing in the other layer, to do the same thing that it's doing now, to tell us the coordinates of the top left dot in the image. But if it's already been identified in that secondary layer, and this is where I'm getting into this Visuospatial Sketchpad idea, is so if it's already been identified in that secondary layer, then tell us where's the next dot in the screen. So this significantly amps things up. Instead of just giving it 2 dots and saying, tell me where the dot in the top left corner of the image is, we're going to still give it 2 dots, but then we're also going to give it the secondary layer that may or may not have a dot in it that will overlap. If it's present, it's going to be close. It's not exactly going to overlap, but it's going to be kind of close with the position of the top left dot in the screen. And in that case, then we want it to tell us where the position of the second dot is. So it has to be able to do that. And so I've generated some data that does this. It passes in 2 layers of data. This is all RGB, so this is the 2 dots here in the blue layer. In that in this new data that I've generated, the green layer is this secondary layer that we're going to use as this Visuospatial Sketchpad. And so the idea is, if we've originally given it 2 dots, it identified the top left dot in the screen, and then we reprocess that image by passing in what we've already identified. Can it then detect the second dot? So in this way, by doing multiple passes of the same input data, we can identify 2 dots, even though our network only has 2 outputs. So we're using a secondary layer to be able to do processing on an image in multiple steps. Okay, so this time, okay, so I'm gonna load what we just trained. I saved that. Now, one change that we have to make here is, instead of receiving a 2 deep in, a 32 by 32 1 deep input, I'm gonna change it to a 2 deep input. So that's basically going to be the only difference. Okay, and I've auto-generated some data. Now, so I'm gonna give it the 2 dot images, just like we had before, without anything in the secondary layer. I'm going to give it that, but in addition to that, I've also generated a version of the same data that does have dots in the secondary layer for the top left dot. Okay, so I'm going to add that to this data. And then I'm going to use the whole thing as the training data. Okay, so one of the changes that I have to make here is I have to clear out the weights on this first layer, because the weights are tied to the input depth. And because we changed the input depth, that the weight values on that first layer are not correct. So I have to clear that out. And then, so now let's train this and see if it can identify. Okay, so I'm going to pause it here. And so what we're looking at is the position of what we're trying to predict is if, so there's going to be, like before, there's going to be 2 dots in the main input, and there's going to be a secondary layer, the layer input depth that we added, and in that secondary layer there could be a dot also close to the top left dot, and if that is the case, then we want to predict the second dot. If there isn't, then we want to predict the first dot. So you get the idea. What we're trying to do is come up with one network that we can rescan the same input image with augmented stuff in that secondary layer, and as we do that, it will move through components of the image, and from moving through those components of the image, we can come up with a more better description of what's actually there. Okay, so right now it's not doing a very good job. So again, the red dot is what it predicted, and like I mentioned before, it's always only going to predict a dot, you know, because the output of the network is just two values that we're doing logistic regression on, and those determine the x and y of some dot in the network. So we're going to leave it to train a bit more and see how it does. Obviously, so you can see here right out the gate that the loss function is actually larger than what it was in prior runs, because this is obviously a more complicated thing. We're not just giving it one dot and saying find the position, or giving it two dots and saying learn the top left position. We're giving it two dots and saying we may or may not have already identified the top left dot. If we haven't, then give us the top left dot. If we have, give us the next dot in the screen. So this is a much more complicated thing for it to learn, but still you can see the cost function is going down, but it will go slower and it plateaus, and we can play around again with these weights, but I don't really care about that. So let's see how it's doing. This is actually pretty good. So see, when it's green, so this is green blue. So again, the top layer there's two blue dots in the main layer of the image, but then in that secondary layer we can, and in this case we do, have a dot that's overlapping or is close to that top left dot, and so we want it to tell us, okay, in this case, where is the second dot? Okay, so this is pretty bad. It got that, and I think the reason is it's hard to tell which one of these is close. Obviously it's this one that's closer to the top left corner, but that's kind of cutting it close. So let's leave it to run a little bit more. Okay, so it should have overlapped with this. It got it kind of close, but at least it's not going after that one. Okay, so in this case, there's nothing in the secondary layer, and we wanted it to tell us the closest to the top left, and it did it, and it got it right. That's right too. Okay, and then here there is something, we've already identified this in the secondary layer, so we want it to tell us the coordinates of the second one, and it got that right. Here there's nothing in the secondary layer, and so it got that right. So we can leave this to learn, to train a little bit more. Okay, so it can probably improve, but it's pretty impressive that it's able to identify that if it's just given two dots and there's nothing been identified in that secondary layer, it should pick up the location of the one closest to the top left. Otherwise, if there's already something there, then it should. Now the question here is it actually learning that, or is it switching whenever it sees anything in the secondary? And that's another question that we have to get to, that it could be some sort of overfitting in that respect. But for now, let's proceed to the next thing. And the next thing, we want to amp it up a little bit more, and instead of giving it 2 dots, let's convert it into a line. So we're going to give it a line, and we basically want to do the same thing, but instead of identifying the dot that's closer to the top left of the image, we want it to identify the end of the line that's closer to the top left. Okay, so we're going to use that same network that we had from before as the base network. It is still going to take in a 2 deep input 32 by 32, and it's still going to output a 2 deep out, a 1 by 1 2 deep output, and do a logistic regression on the position of the dot. Now I've generated some data that instead of 2 dots, this time it's just going to be a line, and we want it to start to identify the position of the top left end of the line. So again, the blue here is the input data that we're giving it. With each training image, we're also giving it the coordinates of the top left position of that line, and we want it to start to learn that. So I'm going to see, can it do that? Okay, so the cost is actually smaller than what it was before right out the gate. So this is likely a simpler task than the last thing that we were doing, which was 2 dots with something in the secondary layer. And in this case, we're going to move on to quickly to the same experiment that we did before, where we add this top left, the possibility of it being identified already in the secondary layer, in which case it then needs to identify the other end of the line. Okay, so this is actually doing really good. It actually does better than the 2 dot case. It pretty closely is able to identify, and track the top left end of the line that it's getting as input. Okay, so let's save this. Okay, so let's load the network that we just saved, just so that the training goes a little bit faster. So we've already trained this to identify the top left end of a line, and what I'm going to do is I'm going to give it the same data as before, but I've also added to it the cases where the top left end of the line is already identified with a dot in the secondary input, secondary layer of input to the image. So in the green layer, there's going to be a dot in some cases already identifying that top left, in which case it has to identify the other end of the line. Let's see if it can learn to do that. Okay, so I'm going to pause it here. So we've already trained it for this case where there's nothing in the second. So you see there's no green here, so there's nothing in that secondary layer, and in this case it has to identify the red with the red dot. It has to identify the top left end of the line, because we've already trained for that. It's getting and it's already starting to pick up that this is what we want it to do. So when it's already been identified, the top left end of the line, then we want it to identify the other end of the line. So see here it got significantly wrong, and so we're going to have to leave it to train a little bit more. But here we've already identified the top left end of the line, and it's the coordinates it's giving us are closer to that same thing, so that's obviously not correct. Again, here you can see that the cost function out the gate is in the 0.4 range, which is double what it was for just the identifying the top left end of the line. And this is going quite a bit slower. This is a very tricky task. Okay, so that took a bit of time to run, but let's see. So the cost functions come down, and it's not great, but it is getting a hang of it. Wow, that's pretty off. It's kind of, it's getting close, but it's still, okay, so this clearly needs more training. Okay, so I had to leave that to run a little bit more. The cost functions come quite a bit down. Let's see, I think it's doing much better now. So when we've already identified the top left in the secondary layer to the input, it should identify the coordinates of the next end of the other end of the line. And if we haven't, then we want it to give us the top left end of the line. So it's kind of getting the hang of it. Okay. So if we were to give this, the thing that I'm going for here is that if we were to give this as the input to this network, it would first identify the top left end of the line, then we would augment the second layer of the input and with the same network, with the exact same, we repass the image with this augmented data, and then we get the second end of we get the other end of the line. And then by outputting these two coordinates, we basically get where, you know, the length and the position, the direction, everything of this line, as as information of what is in the image. It's a line that starts here and ends there. That's like some tangible information that we got out of this network that only has two logistically regressed outputs. And so now what we want to do is extend this. What if we had two lines connected? How far can we take this? Continue. So the next thing we want to do is give two connected lines and see again, can we get to learn first the top left end of those two lines, and then we'll then train it to give us the next positions, the next inflection points in that line, in those two connected lines, as we augment the secondary layer of the input with that information. Okay, and so I've generated so I'm going to load the network that we just trained that detects the two ends of the line depending on whether we've given it or, you know, the top left end of the line. And I've also generated some data for two connected lines, two line images, and I'll share this training data. Okay, so let's pause. So we've amped it up obviously here. Now instead of one line and it identifying the top left end of it, there's two connected lines, and we want it to identify the top left end. And it's not too bad right out the gate, because we are giving it the network has already been trained to identify the top left end of the line, so it's kind of getting a hang of it pretty fast. It seems like when there's like a V type of thing, it gets confused and is not sure which end to tend towards, but we can leave it to train a little bit more. Just going down fast. Okay, it's not too bad. It's picking up on what it's supposed to do. Seems like detecting the top, just straight up detecting the top left end of a line is a overall easier thing for it to do. It pretty consistently does it with a single line, and if you have two connected lines, it still is pretty good at identifying this, even compared to the two dot scenario. Okay, so let's amp it up a little bit more, and like we did with the two dot case and the one line, what we're now going to do, and again, so this is the same network that we had from earlier, and it's obviously taking in two input layers, and now in this case we're not even using, there's nothing in the secondary layer, we're never giving it anything there, and that's why it's always, we always want it to identify the top left end of these two connected lines. Oh, and by the way, this data that I generated, it does have restrictions, so that there's no, one end of these two doesn't get too close to the top left end, so it becomes confusing or anything. There's a certain degree of an angle that has to maintain. So that depending on how close you let it get, there could be, you could argue that there could be some overfitting going on there, but let's ignore that for now. Okay, so let's load that network that we just saved, the two-line detection thing, and I've generated some data. So we're going to give it the same two-line data that we had, that we just used, and I've also generated ones that have already identified the midpoint of the inflection point of the two lines, and then one where we want it to one where we've already identified the top left end of the two lines, one where we've already identified the top left and the inflection point, and then we want it to identify the end of the two lines. So it's the combination. So it can be any three of those combinations. There's nothing in there's nothing in the secondary layer, or in the secondary layer we've already identified the top left end of the two lines, or we've identified the top left and the midpoint, and then we want it to identify the end. So this is a much more complicated thing for it to identify. But if we can get to learn this, then it's awesome. Then we have a network. We can give it, multiple connected lines. It will first identify the top left end. Then we add that data as the secondary layer to the input, and we repass that same input image through the exact same network. And then it will identify the next position, and then the next position in those connected lines. And in doing that, in each iteration, we're ending up with these coordinates that tell us the length and position of lines in this image and how they're connected to each other. Okay, so I'm going to give it that as the input, and we're going to use the two-line thing that we just trained as the starting point of training. This takes a second to load because there's a lot more training data. Okay, so let's pause it here. Okay, so as I mentioned, so again, it's going to be two lines with an inflection point. If in the secondary layer we've already identified the top left end of the two lines we want it to identify, but if we haven't identified the inflection point, we want it to give us the coordinates for that, and that's what will be in the training data. But if we've given it, then we want it to identify the other end. Okay, so that's a tricky one because it's not an inflection point really. Okay, so this case, there's nothing in the secondary layer, and it's kind of getting close to it. It has to give the coordinates of the top left position. Again, that's basically a straight line. Okay, so this is an example of we've given the top left in the secondary layer, and we've given it the inflection point, and it's supposed to identify the other end of the two lines. So let's leave it to train a little bit more. Okay, so in any case, now the last step in this is we want, so going back to the network topology, so the only thing we're outputting so far has been this, the X and Y coordinates. So we only have two output values, and we're doing a logistic, sigmoid regression or something on it. Now, for this to actually work, to construct a Visuospatial Sketchpad with, that track different positions, and from those we can end up with something that's deducible from the image. Because this is an iterative process, we need to at some point be able to say, okay, I'm done. I've found all of the inflection points or the dots or whatever it is we're looking for. I'm done. Let's stop this iterative process. So I think what the network also needs is an output in one final output that says, is this the end? Is this the last thing that I've processed? I think I've got everything covered. And this is a tricky one, because this determines, do we take the output that we have so far in that secondary layer and and pass it in along with the original input again to augment that secondary layer further, or do we just take it so far and try to, from that, deduce what it is that we're looking at? So the thing that needs to be added here is I think so the output depth needs to become 3. We'll train the network to identify not just the coordinates of the next position inside the image, but also whether that's the last one. So, if we're looking at a line and it's the first time, there's nothing in the secondary layer of the image. So we're going to identify the top left end of the line, and we should and the output should indicate that this is not the end. There's more coming, and so it should be able to learn if we are not at the end of the very last line, it should not trigger that output. And that's what I've augmented the data with. And so the training data, I've generated the same training data with 3 outputs. So and it's only in the case where 2 inflection point, the top left and the inflection point have already been identified in the secondary layer. And we want it to identify the last ending point. Then when it predicts that, it should also predict that this is identify that this is the output. Okay, so I am going to save this. As I mentioned, I've added that information, the third data value to each sample data, indicating whether it's the last dot to be identified in the image. And I'm going to load the same training, the training that we'd already done for the same network, and the only difference is, it's gonna, so we have to clear out the last fully connected weight values because now its output is different, so the weights would not be correct. But now we have 3 outputs. The first 2 indicate the x and the y coordinates of the next dot that we want to identify, and the third value again is going to be a logistic regression on a 0 or 1 value that indicates whether this is the last dot to be identified in the image. And so now when this runs, we're not going to be able to see that third value. And so what I've done in the image is, what we'll see in the image is, as before, the predicted dot is going to be shown as red. But if it's the last dot, then I'm going to show it as orange. So there's that implemented. Okay, so this is the orange case. So in the secondary layer, we've already identified the top left, the inflection point, and we want to identify the endpoint, and it's correctly detected that this is the last one. And so it should be orange. Now, one concern here is that, is it really detecting that this is the last one, or is it just detecting that there's 2 dots in the image? So if we extend this to the case where there's multiple connected lines, will it still think that it's reached the end as soon as it sees 2 dots in the secondary layer? So that is one concern, and so we have to see if it's generalizing as we intend. So you can see this is a much trickier task even than the last one, because now we've added this third output value that it needs to regress on. So see here, it's not that this is not orange. It should have identified that this is the last one. So it got the endpoint pretty well, but okay. So in this case, it's still mixing up the endpoints. So I'm going to leave this to run for a bit. Even though we did use the pre-trained values, the thing is we had to clear out the fully connected weights because its output depth had changed, and so because of that the error cost has gone way back up. So it's going to take a while for this to... Okay, so I'm going to have to leave this to train some more. It needs some more training. But in any case, I hope you got the idea. The aim is to be able to create this Visuospatial Sketchpad as a secondary layer into the image that we reprocess it again and again, augmenting that secondary layer, and in the process we end up with these coordinates of points that are somehow related to each other. Now obviously in this simple case of just lines and dots and stuff, it literally means that these lines are connected, but in a more complex image, the connection between the dots can be more involved. Now to expand on this, to make it able to detect the handwritten numbers, the next step would be to identify arcs in these. So be able to, so until now I've only been looking at straight lines, but what if there's an arced line between two dots? Next thing, I have to generate images with arcs between them, and then get to learn the start and end points of those arc lines, and then multiple arc lines and straight lines. And once that's done, then I should be able to feed it the MNES data. That's what the aim is, to go then back to the MNES data and be able to get to do one-shot learning, basically, by telling it specifically what type of connections between inflection points and what types of lines with what sort of arc between them would constitute each of the different numbers in the MNES data. So thanks for watching, and let me know if you have any questions or ideas about how to improve on this approach, and in a later video I'll update on how it proceeds with adding arcs and extending it then to detect the MNES handwritten numbers. Thanks for watching.